Good morning, everyone. It's my pleasure to have Professor Oussama Khatib give a talk today here in the Maryland Robotics Center, and I'd also like to thank Technosciences for the generous sponsorship of the seminar series. So Professor Khatib is a very, and I cannot stop, very well-known roboticist. Very famous. He's been instrumental in several robotics initiatives, right from, I would say, I actually don't want to guess the number of years, but he's been extremely influential in the robotics area. His research has focused on humanoid control architectures, human motion synthesis, interactive dynamic simulation, haptics, human-friendly robot design, and so on and so forth. It goes on. He's co-edited the Springer Handbook on Robotics. If some of you have seen that, it's a Bible in terms of the information that is there in that. I think 1,000+ pages. He's a fellow of IEEE, and he has served as the RAS as a distinguished lecturer. He's a member of the Administrative Committee, Program Chair for ICRA 2010. He is the President of the International Foundation of Robotics Research, which a lot of you know is the founding body for robotics activities, and he's also the recipient of the Japanese, of the Japan Robot Association Award in Research and Development. He's also received most recently the IEEE RAS, the Robotics Automation Society Pioneer Award in Robotics and Automation for his fundamental contributions in robotics research, visionary leadership, and lifelong commitment achieved to this field. And I could go on and on. So I think with that I'll stop and have them start his talk, which is going to be very exciting.
Thank you so much. Thank you. It is really a great pleasure to be here. This is my first time to Maryland. I cannot believe it, but yes. So thank you for this opportunity, and it is also a pleasure to be here on your campus, your center. This is really a nice initiative. I was discussing yesterday with Jaydev about the effort in robotics, and I was really impressed by the number of people involved in robotics here. This is really wonderful. Robotics is growing, and it's growing outside of manufacturing. In the 80s, robotics was confined to deal with offline issues where we programmed the robot to perform tasks where human already were just outside programming. And today we see robotics taking us in many different applications where the human is really in the center. So let me start with history. Actually, I have a short video here. This is from the probably first years I arrived to Stanford, doing compliant motion, force control, contact, and this is me. And the idea of using sensing with robots is very important. The idea of understanding contact and collision, the idea of interacting in real time, creating cooperation between robots through compliant motion, force control with the human, dealing with the dynamics of macro mini structures, modeling complex objects that are interacting, controlling redundancy. This is becoming redundant robot, although it's not redundant for that task. Then going to mobile manipulation, exploring the world, and also doing a higher performance force control through that feedback, building robots that are more capable of force control, dancing. So these these were really the early development that brought more and more feedback in those systems, more intelligent algorithms. This is actually an algorithm for collision detection that we will talk about later as we go to discussing haptics. So robotics, as I'm saying, is really in a completely different picture today. The picture, in fact, is that we see the human around the robots. The robots is extending the hand of the surgeon to operate, assisting a worker in its task, exploring new spaces. Now, this is great. This is bringing a lot of new challenges that we need really to address, and we can not think about deploying those robots next to the human unless we address all the different issues that we need to resolve. Safety. Are we sure that we can be next to this robot and remain safe? Safety is really a challenging problem for humanoid robotics, for robots interacting with humans. And the problem is coming from the way we design those robots. In fact, we pursued the same concept that we had with industrial robots, gears, transmissions, and we continue that to humanoid robotics. But let's really make sure that our robots are safe. We saw a lot of humanoid robotics performance, especially in free space. So these robots are moving, running, going upstairs, doing different free space tasks. But how can we really use these robots in our world? How can we make them useful by letting them interact with the environment? And that is really a question that is still very difficult to answer, because these robots can walk, can do the mobility part, but can they do manipulation? And doing manipulation means we really need to understand balance, reaction forces, how we can maintain the capabilities of those robots to perform while balancing. So there is a need to create a framework that addresses the problem in its of bringing together mobility and manipulation in a framework that is unified, so we account for the balance while we are doing manipulation, we account for the manipulation while we're moving. And bringing those capabilities to the robot is going to require perception, it's going to require capabilities of interaction, new algorithms, new strategies, especially compliance. And compliance now is very different. It's not the compliance we used to work with when we were controlling one point contact or one object in contact with the environment. Now the robot is immersed in that environment, and it needs to control multiple points of compliances while doing the manipulation. So that is going to require us to think about the whole body contact. So imagine you're having this robot, and you're going to ask let the robot sit, relax a little bit. And it's very hard for a robot to sit. It's true. I mean, you have all these points. How can you create compliances at multiple points that are consistent, that will not fight each other? And because compliance means you are not rigidly controlling positions, and if you're not controlling the positions, it means you have really to sense different locations, to determine the normals, etc. Well, I was mentioning yesterday, this work comes from almost like 10 years of development, and let me show you the result, and then we can go back to the different issues involved. So here's the robot compliantly moving, guided by the human, and we are able to teach the robot how to move, how to make contact at different locations, and also we are being able to now not only create compliance, but use the compliance in the learning process. So we are teaching the robot how to reach, where to grasp, and how to manage a load while it is moving. So these capabilities are going to bring a lot of issues, as I said, from the perception to the algorithms, to the skills the robot has. So in perception, we need to first know the free space. The free space is very important in order to navigate in that environment. But if we are going to have contact with the environment, then we need to also to navigate in the contact space. And the contact space requires not only locating the contact points, but also finding the normals and understanding the context of that interaction. Well, it means we really need to have multiple modalities of perception. We need to be able to have tactile sensing on the body. We need skin. We need all kinds of different proximity. We need to merge all these different information of the interaction. So we need really to think about a robust way of doing that. And probabilistic techniques has been quite successful in merging, fusing sensory information. So once we have that information about the interaction with the environment, the context where the robot is, then we can think about how we now are going to use it in real time to perform those operations. We need to control the robot at those points. We need to be able to make contact, balance, and find the center of mass, and we need to put all these different things in one framework. So the challenges, again, in summary, the challenges are how we create sensing together with the different modalities to perceive the state of the robot in this unstructured environment, and to do that very quickly in real time. How we plan, how we control, and how we do that without resorting to the lowest level of control. We do not want to work just with the joint motions and have to plan all the detailed motion at every time. So we need to develop skills. We need to plan with strong primitive to allow us to quickly adapt to the changes in the environment for systems with many degrees of freedom in mobility and manipulation. So learning is going to be very, very important, and we need to also understand the interaction between the robot and the human, not only the physical interaction, but also the cognitive interaction that will take place. We need to build mechanisms that are safe, but not only safe, we need also to create mechanisms that are capable. And actuation is a huge problem. How we, probably when we think about the problem of safety, so if we think about safety, if we think about the ability of the robot to interact with humans, we need human-friendly designs, and we need algorithms and techniques that allow us to create interactivity between those robots and their environments. So let me just go quickly over issues of design in terms of the safety. So when we were working with industrial robotics, we were saying, well, when the power is on, no human are allowed next to the robot. And even we would put the robot in a cage. So just in case something would break and flies, it will not hurt anyone. Now that we are contemplating having those machines in our homes to assist, to help, to bring entertainment, whatever, safety becomes a really serious issue. And the challenge is not really just safety. The challenge is how can we build a system that is capable and safe. Because in the design, the two are always competing. So just to underline the problem, transmissions are a large part of the problem. But transmissions are maybe the problem, but the cause of that is really the way articulated by the systems deal with the gravity in our planet. The problem is when we are designing a robot, we need to carry a load by a link that is connected to another link that needs to now carry the load with the link, and you end up with those large requirement in torques. So to make our robot compact, what we do is we put higher and higher gear ratios. These gear ratios are going to reflect the inertias. The rotor inertia is reflected by the square of the gear ratio. So when we are dimensioning our motor, we are going to end up with a continuous torque requirement to deal with whatever load the links we are carrying. And once we dealt with those static problems, we say now this motor has also to deal with the accelerations, the performance, the responsiveness. So in this motor, we are putting all the requirement, and we end up with a large motor, which means we are going to have a rigid, high performance, rigid reflected inertias at contact, and then we end up with an unsafe robot. Well, if we study this problem in the frequency domain, we notice that immediately that the torque requirement are really high in the low frequencies. In the high frequencies, we need much smaller torques, which brings the requirement to be much different from what we would imagine if we had just one motor. So if we bring two motors, we will be able to work with a big and a small motor in a very different way, because now we can place the small motor on the structure, which without reflecting large inertia, and putting the big motor in the base. This big motor does not need to be high performance, so we can decouple it. And the inertia coming from that motor will not be reflected when we have an impact. So that was the concept of distributed macro mini actuation that we call DM2, that led to a really interesting design where the capacity of this robot is almost like a large robot, but the safety and the performance are like those of a small robot. Now, this design was completed with multiple arms. We used it in different contexts, but the design itself, putting those couplers, elasticities, driving the joints with cables, all of that brought a lot of complexity. And we thought there must be a different solution, a better solution. The solution we explored next was inspired by this design. All of us know about pneumatic, fantastic, pneumatic are safe, etc., but compliant. But then we have the problem of dynamic responses. That if we replace our macro motor with the pneumatic, then we will be able to create a system that is very responsive, and this is an example of a platform that we built capable of doing force control with capabilities almost like a Puma, but with reflected inertias, effective inertias that are so small. So if we take the Puma, we get like 35 kilograms at a contact. This will have 1.2 kilograms. Huge amount of reduction with high performance. We started to explore this direction further. We worked with a group of Mark Tusky building shape deposition manufacturing techniques to integrate these different components in bone-like structures. So we have very small pressure amplifiers integrated inside the bone with muscles and with an integration of the pneumatic actuation inside a cover which is sort of skin around the arm that provides not only protection from the first impact, but also sensing. That is, we are able to sense contact and able also to even sense proximity. So this is a very promising direction of building, thinking differently about the design of robots, in fact, and going beyond the way we build robot with always one joint, one motor, gear, transmission, going with different solutions to explore how ultimately can one build a robot that is safe but also capable. So this design is leading now to this structure. We built the shoulders and elbows, And we have a complete design that is based on the concept of combined pneumatic and electrical actuation. Pneumatic could be, the pressure could be carried by in a bag behind the robot, like in the case of Ashimo. I mean, every robot has its power. So here, instead of the batteries, we will have the air pressure, which could provide, I mean, enough autonomy. And then we will have a system that is safe, especially with those sensors that are providing also information about the proximity of obstacles and potential danger of collision for the robot. So this effort is ongoing now in Europe. There are a number of different programs. France is one project that is bringing about building safe new robots. There are also efforts in Korea, in Japan, as well as other efforts in the US. Last week I was in Houston at the laboratory involved in building Robonaut, and I'm not sure if you have heard about Robonaut 2, which is going in this direction of creating compliance. If we are to interact with human, we really need to deal with the compliance, with the safety of the robot. So safety is very important, but also we need to make use of it and control the robot system. So we started exploring the space of human, deploying a robot in the human environment in the mid-90s. And we took this to be a very straightforward design platform, which was holonomic mobile-based combined with a Puma robot to bring this integration of mobility and manipulation. Let me show you a short video illustrating the early work and then go from there to show you the development. So the idea here was, how can we bring mobility manipulation in one system that is working in the human environment? So the idea was not to say, I'm going to move, manipulate, but really to do this manipulation and mobility together. So here we are talking about tasks that involve bringing the robot to hold an object, to manipulate an object, so this is the task. But at the same time, the robot needs to be able to adjust the posture and move from its configuration. So in this motion here, we are bringing two controls, one for the task and one for the posture. They are decoupled. And it's sort of like decentralized control, one for the posture, one for the task. And now we can generalize, because the task here is the carpet, and the posture is keeping a distance from the hand. And simply with those two combinations, we are able to do a lot of different useful things. With force control, we can contact the environment, we can make this contact, and we can then perform all kinds of tasks, such as ironing my shirt. This is, I think, the only shirt ironed in the world. but only one time. Well, this is one of the most difficult tasks that you can imagine for a robot. I mean, you can see the base is moving, the arm is moving, just in response to the touch of the human. And this is compliance with all the coordination, internal force control, vectors manipulation, and well, we still needed vision here. So those ideas were being explored in the mid-90s. In fact, we were thinking about those systems as a system to the human. So these robots were the muscles, provided the muscles, and the human provided the brain, human-guided motion, and essentially putting the two together to create that synergy between human and robot. Now, those capabilities required, as I said, compliance and responsiveness. We went as far as making the robot dance with the human. I mean, who wants to dance with a robot? But the point here is all the compliance. The robot is responding to the touch and moving almost like a toy in the hands of the human. So with compliance, we can change completely the way we are interacting. And this was really the point that was brought to the attention of the Honda project. This was done around 97, 96, 97, and those of you who remember, 97 was the year when Honda brought P2 and built the first humanoid robot that can go upstairs without falling in. But that robot didn't have any capability in really manipulation or interaction with the world, and Honda was very, very interested in bringing those capabilities. But the challenge is huge. I mean, if you think about cooperation between multiple of those robots, if you think about interaction between those robots and the environment to cooperate and manipulate, it's going to be really, really difficult, because now we're not talking anymore about one point, we're talking about multiple points to be controlled, and we are talking about a lot of constraints. Those robots bring all kinds of internal constraints, self-collision, obstacles. How can we move to perform a task, change the posture, while maintaining, making sure that our motions are consistent with all these constraints? How can we also perform postures for the robot, and while also maintaining those constraints? So it seems like there is something about sort of hierarchy in the control that needs to be developed, and this is the sort of development that need to be implemented in branching structure now with under actuation, because it needs to balance all the time. So to address those issues, we need to think about whole body control, not anymore just controlling the inner fracture or the gripper. We are talking about building those capabilities while dealing with constraints, multi-contact, internal forces, and the balance while building those manipulation skills. So humans are completely in the center of this, because building those controllers for robotic systems means we really need to look closer to the human. In fact, even when we were working with those robots, we were working with inspiration from the human motion and the human way of controlling. Most robots are controlled by thinking about the inverse kinematics, which allow us to imagine the final configuration that we are going to reach, and we interpolate between these two configurations to find all the joint motions. Well, humans do not do that. I'm sure if I give you this, you're not going to find that final configuration. What we do is essentially we visually servo our hand to reach the goal. So we are reaching this goal, and the body will follow. We do not know exactly that configuration. It doesn't matter. We have that behavior that adjusts the body to reach and to accommodate the needs for the task. So this is something that humans do, and we needed to really to further explore that direction to find more about the posture, about the characteristics of human motion. We were not interested in just like taking the human motion and copying the human motion to perform a task. But we wanted to understand what criteria humans are considering when they are moving, and what is being involved in those motions. So we started a study to analyze human motion. We started a study to model the skeletal system, to model the muscular system. We worked with a group in biomechanics, the group of Scott Dell, who provided us with a lot of data to build those models. And we collected a lot of data on subjects to explore what is going on. Now, the study brings something very simple and intuitive about human behavior. And when we are learning a skill, what is going to happen is that we are going to discover the most comfortable way, the most effective way to perform that skill. And this is clear in here. We can see that immediately as we reach to carry a load, we adjust our body to to balance the different effort exerted by the muscles to produce the forces needed for that task. Well, let me just talk about the conclusion of the study. The analysis we have pursued showed that essentially what humans do is they like what we do with the robots. With the robots, when we are going to use the robot, we try to find the best configuration for the robot to perform the task. We call it mechanical advantage. Well, humans discovered the physiomechanical advantage. And the physiomechanical advantage means we are maximizing the transmission from muscles to the task, the forces required for the task, which means we are minimizing the effort. In fact, we are minimizing the pain we feel about performing the task. And in high performance motions, like when we're playing in sports, when we are throwing, we really learn how to do it. It's not straight line. It goes through specific trajectories related to the way muscles transmit the forces and create acceleration. So this is being done obviously within a number of other constraints, but the result is we can capture those characteristics through some energy representation, and then just by using that energy we can minimize the energy to move to capture the human motion and understand how it is taking place. This study, in fact, led to a sort of very simple criteria which can be understood by, if you think about this effort minimization. So let's take one muscle, M, and imagine M is the effort exerted by the muscle. If you are minimizing the energy associated with the muscle, you are going to be minimizing M squared. Will be the square of the tension, M. And you have big muscles and small muscles. So as a result, you're going to be weighting that criteria by the capacity of the muscle, C. So the energy that we speculated about is simply this combination of M squared and C. And the energy is, are you ready for this? I'm not sure. Do you want to know what you're minimizing?
Yes.
Yes? Okay. All right. That's what you're doing. So, if we go to multiple muscles, this is in fact a quadratic form on the task, on the forces that involve the task, where phi is capturing this Jacobian matrix, I would call it the Jacobian, the matrix that connected towards the joints to the forces. But more than that, this is the mechanical advantage. But the physiology is very important. That is the transmission of muscles to those joint torques. You have multiple muscles affecting a torque, and the configuration of the human is going to be very important in that minimization, in addition to the capacity of the muscle. Now, you do, I mean, human all the time are doing things without thinking. You know, when we are taking a cup of coffee, drinking a cup of coffee, we often we don't have time to go over that exercise. Usually I do the exercise and everyone would notice finally that there is something really specific about human. I mean, if we go at this exercise here, you will find that everyone would go like this, 42-degree angle. And this 40-degree angle is not an accident. It corresponds to a specific value of this phi. That is, at 42 degrees, you get the minimal quantity in terms of performing, carrying a load at this location. If this load increases, this angle is going to change. And when we add weights at the hand of the human, we observe that changes in the angle. In fact, you observe it in many different situations, and it makes all the sense. What is now interesting is that we can capture those characteristics, and we do not need to capture the motion anymore. We can go and perform motion using the balance, using the dynamics, using those minimization to guide the motion. let me just show you what I'm talking about here. I'm going to, this is a robot, and this robot, let's say we would like to move it here. To move it here, we're going to have sort of this guidance, some attractive force that will pull the hand to the goal, that immediately we need to balance. So you see the robot is moving, and it's also balancing. This is a dynamic simulation, not just kinematics, but the whole dynamic with the simulation. You can see the robot is just in real time following my guidance here. And in fact, this robot, I mean, if we drop it, you can see it's falling. Here it falls without any contact. Here it will fall with hitting a joint limit. And as I said, this control is decoupled. That is, the posture is decoupled from the control of the task. So if we pull on the hair, you can see the hands are fixed. If you pull here, the robot is responding by adjustment. So this is the idea we are showing here, that is we are guiding the motion, and you have all these other joints coordinated to perform and optimize the motion. So the robot can now follow the human. As we understand the human motion, we can not copy the trajectories, but really map those characteristics to the robot. And this is what we did with Ashimo. Ashimo here is moving, and despite the fact that Ashimo has much less degrees of freedom, Ashimo is quite fluid. It's not like walking over a trajectory, it's just like moving to the task and adjusting its posture very simply. So what happened was, well, this study was meant to understand the humans so that we can better control robots, but it is clear that there are a lot of interesting things that could be applied to the human independently of the robot. So we pursued this study in the context of trying to understand the human motion and trying to see what is going on in those high-performance motions through the dynamics, through those trajectories. And what we started doing was to hire our athletes from Stanford to work with us and perform those high-performance motions, and then try to collect data from marker motion and then analyze those characteristics. And again, we find the minimum muscle effort minimization on those trajectories, that is along the ellipsoid associated with phi. You can see those motions. You can see it also in another characteristic, which goes further. In robotics, what we do is we look at the torque limits, and which are bounded by the motor capacities, and then we map them to the acceleration available at the end effector, which are bounded again in different directions. So for instance, for the Puma, you can accelerate much more in this direction than this direction. Well, let's see for the human. Well, the human can accelerate much more in this direction than this direction. And this is why when we are throwing, we are following those lines of acceleration. We do not throw in a straight line. But this is really specific to every subject. So what we need to do is to analyze those characteristics for a given subject, and then our thought is that we can build the atlas, and then we can use that information to feed back to the human corrections in their learning of a skill. So if we are able to observe from marker motion in real time, then we can do that in real time through visual and tactile stimuli feedback. So we started looking at golfing, starting looking at different motions, and we developed a technique to track human motion in real time. The concept uses this task-oriented control concept with a hierarchy that allows us to, in real time, to track motion. Here's an example of tracking of the motion of the hand with a millimeter of error. This is done in real time. Essentially what we are doing, we are controlling the model to track the configurations of the markers, and this is providing now all the dynamics of the human model, human motion on that model. This is an example that was applied to dancing. This is African dance, and from markers we are able to reconstruct that motion. So if we go to the markers, here is the reconstruction, and from the reconstruction now we can display this in different conditions, different constraints, and different numbers. So once we have the characteristics in real time, as I said, we can use a stimuli to feed back to the human, now to teach, to correct motion. This is very interesting, not only for high performance, but in injury prevention, in many different areas that are going to allow us to have insight into the human motion. We are building all kinds of devices, including devices like skin stretching devices to indicate direction of rotations and allow us to bring that feedback, tactile feedback to the human. Well, I'm going to move to another topic because the time is, what time is it? All right, so I mentioned about concerns, but this is really probably one of the most challenging problems with the control, because it is not enough just to move. You need to make sure that you are not going into any joint limit or self-collision, and that means we need to understand those characteristics. So now we need algorithms, very, very efficient algorithms to find very quickly what is going on. And we developed collision detection algorithms, we developed collision resolution algorithms that allow us to do a lot of those things in real time. Those algorithms has to deal with multi-body collision, not point-to-point single object collisions. We're talking about multi-body collision in real time. And those concepts are based on a different way of representing dynamics to remove the dynamic representation in joint space, which makes it very, very hard to resolve collision. We are representing the dynamics at the contact point immediately and reducing the problem to a problem of effective mass collision, that is collision between two masses. And when we have multiple of them, we are able to resolve them very quickly. Here we see an example of thousands and thousands and thousands of collisions being resolved in real time. This is quite remarkable. This was done some years ago, and this was the basis of a lot of the work we've been doing in haptic interaction, haptic simulation, display of contact, reconstruction of the surfaces as we move on a contact to find the normals, reconstruct the surface, and build those characteristics, which we are using now in 3D imaging. We are looking at haptic interaction to create from data with pregnant women the information that could be now represented in 3D. So we are taking slices one after the other and ordering them to build the 3D image and reconstruct this haptically. In fact, haptic interaction is used also in skill acquisition through learning by bringing the human to teach the virtual robot that task and extracting the characteristics of the motion. Well, another critical aspect of this is obstacles. So we not now touching how we move around obstacles is a very critical part. Let me, I think I have this. So here is the robot, and if we move, so this is as before. The robot is moving here. So imagine you have an obstacle, and And imagine this obstacle comes next to the robot. We need to make sure that we feel the obstacle, we find those distances, and now we effect the motion. And to effect the motion, we create sort of a repulsive force, so attractive force toward the goal for the hand, repulsive force for the body to move around the robot. So when obstacles are coming closer and closer, the robot is going to move. And as soon as the robot is able to restore its configuration, it will do it automatically. So this interaction is done again in real time, and this is very, very important in those capabilities to bring those interactive adjustment to the robot motion. In fact, this reactive behavior is also integrated within the global behavior, that is a plan that is now modified in real time. And again, the modification is based in local representation of the free space. So here is the free space in green that is modified, and a new trajectory is generated automatically. This is what we call elastic planning. These are very, very important algorithms in making the robot evolve and move in the human environment, which is always changing, which brings always uncertainties and a lot of errors. Now, finally, a major problem that you need to deal with when you have robots like this is the problem of balancing. Because balancing is essentially a large part of the controllers, and maybe sometimes is the only part besides creating a gate and maintaining the balance. The balance is done simply by using ZMP zero moment point. But if we think about interaction with the environment, immediately we have reaction forces that will tip that balance off. And the only way that we can really perform contact is to understand how we can move, we can understand the space in which we can move without reducing forces or accelerations along the normals. And also being able to separately control those forces. We created models that allow us to essentially control these internal forces, control the contact forces, while controlling the interaction forces with the environment. When you are touching the environment, you have moment to control, you have forces between the different contact points, and all of these now can be merged together. We can control a task with the posture, with the constraints, and with the contact at multiple points. We are controlling all the different normals and also the balance. What is really interesting is that through successive representation that brings the posture, take the task, we are able to do successive projections in the null spaces of each of those representations to build that hierarchy. So a posture is consistent with the task, consistent with the contact, consistent with internal constraints, and everything is consistent with the balance. The result is very simple, because we are now talking about just one point, varia, sorry for the math, but we have just one point in high dimensional space, capturing all these different characteristics and looking at not only the state of the robot, but the state of the robot embedded in the environment for the given task. And from one point in that high dimensional space, we can have the dynamics, we have the control, we have the torques that are needed, and we are able now to control the robot in that way. I'm going to show you this live, because this is really unique today in terms of the capabilities of a robot system to interact with the environment. We can see it. There is a robot behind here, and this is running on my laptop. I can't believe it. So you're going to see the robot is detecting the contact, going to find the center of pressure. Immediately it computes the reaction forces, and now it's applying the forces and moving. And if you If you apply any external force, immediately the robot is going to adjust. You can see the robot is, I'm pulling a little bit here, and immediately the robot is adjusting. So if we, and this is very robust, if I apply, if I pull on the feet here, the robot goes back and puts that foot. Wow. Amazing. Amazing. Okay, so what is really amazing is that we are dealing with all the different, so many robots are controlled by, okay, I build a controller for the arm to move, I build a controller to make it walk, I build a controller to make it balance, and try to put them all together, and they start fighting. What we have done here was really to integrate all the different aspects in one framework. And that allows us to get that kind of robustness because everything is adjusted to the changes in the environment, and every aspect of the control is accounting for every other aspect because of the interactivity and the interaction between the different dynamic motions. So a key aspect of those systems is the torque control, the ability to control vectors of torques at the same time at all the joints of the robot. And this is very, very important for many different reasons. Unless we do that, we cannot really achieve those kind of controls. And a robot like Ashimo doesn't have torque control. So we came up with a way to implement torque control virtually on this robot through a transformer that transforms torques to position that could be controlled by the Ashimo controller. This transformer essentially reversed the controller of the robot, and Honda gave us access to their controller so we could do that. So this is the result. The result is that now Ashimo is becoming like gentle. I don't know, have you ever been to a show, Ashimo show? Well, if you go to an Ashimo show, they tell you, with Ashimo there is one rule. Don't touch it. Don't touch it. And we just show them how much you can touch this robot. So now Ashimo is touchable. You can guide the motion. You can teach the robot how to move. You can teach the robot how to coordinate the two arms to carry an object and lift it. These are very new results that we finally were able to implement and obtain with the robot, and also show to the public. I mean, we have not been able to show earlier a number of those results. Now we started also integrating mobility and manipulation and putting all the components together. So the robot now is not controlled to follow a trajectory. It's controlled to achieve a task. This task is part of the plan that is specified by the higher level in the control, and the robot is just performing the task by sensing the forces, the contact, understanding the context, and then being able to perform these different things. I mean, look at the body motion here. The robot is just like following whatever guidance, and it is able to be so soft in its motions. So this is what we have. We have a whole system that allows us to plan very complex behaviors and implement them all in a unified fashion in those fast loops. We have the perception, we have the action. Here, we have here this level varia that allows us to take a complex skill and implement it. But this skill is coming from a level that is processing the data at feature level to understand what is contact, what is normal, what is surface, and then produce those actions. And now we are able to plan not in detailed trajectories of the motion, but with those skills and those primitives. So this is a little bit the public display of Asimov. Anyway, I'm not going to go through this movie. This is a lot of fun with a lot of interaction between students and Asimov. I just wanted to mention this is many years of work with many students. Not all of them are here, and I'm sure. Any one of you ski here? How many skiers we have? Okay. Well, let me show you something. So this is a robot skier. But please do not do that. Okay, thank you very much for your attention.
Thank you for a wonderful talk. Any questions? Sometimes
I see in the simulations you consider basically every contact force and dynamic, but that's simulations. What kind of disparities between like the sensors that you have for touching and?
So in simulation we have models of sensors, and the sensors model are sensing with an error that is introduced from the actual forces. It's like in our simulations, our dynamic model has errors in the estimate of the masses, and so that is in the simulation. But in the real implementation, the robustness of the system has to be much bigger, because there are a lot of nonlinearities. As I said, we are using a virtual torque controller. We do not have access to the torque sensor. In fact, because of our work, Honda and other developers are now exploring the development of joints that has torque control. Torque control is essential. But without torque control, we can manage. And you could see how robust the simulation are. Still, in the real systems, that robustness is not enough, because there are a lot more of uncertainties and model dynamics. I mean, we model robots like with just the rigid body part, but about the higher order dynamics that is not modeled. So robustness is very important.
What's a task in general?
What
is a robotic task in general?
Yeah, so a task is going to involve all kinds of things, but most of the time it will involve motion to some location with contact with some surface or with some object. So a task could be opening this, or this is contact control. So I have to create that interaction, or placing an object, or making some coffee, or doing, as we saw, some interaction with other objects or tools. And the problem is always that you cannot a priori determine all the aspects of what is going to happen if you are in the human environment. If you are in manufacturing, you can define precisely where you should be, at which location, in which orientation, and then you can pre-plan everything. In the case of a human environment, I do not want to be able to open this bottle only. I would like to be able to open all kind of similar objects, and this is a skill.
So I understand. So the task for you is to guide something externally from object.
Yeah. So it involves motion and contact, basically the task. But with the ability to avoid collision, obstacles, and avoid hurting, touching colliding with itself, so self-collision, and also internal constraints. So you have these, a robot is all these links connected that are evolving in space, but under so many different constraints, and you need to coordinate the different motions. So you can think about this problem as an optimization problem under constraints. But if we do that, we will spend our time just optimizing. We will never reach, I mean, it is so complicated because the space is so big. So what we're trying to do is to have common sense intuitions from the human to build controllers that can be really effective and work like human, and which makes them compatible even with human. Yes.
One last question. Yeah.
So you said that you studied the human, try to understand the human in order to better control the robots. Do you ever find that building a robot helps you understand the human more?
Thank you for this question. This is actually maybe the biggest aspect of robotics. We think about robotics as well, robotics is only about robots. But what robotics showed us is that our study of articulated body systems brings models, tools, algorithms that are amazing to study human, that are just like unbelievable. In fact, in the area of biomechanics, a lot of people do not have those tools. And when we started implementing human model with our tools, we have been able to create those real-time human motion reconstruction that couldn't be done before. Finding the characteristics, the dynamic characteristics, the physiology in real time is just amazing. So robotics is not really about just robots. It's about many areas that involve articulated body systems, high-dimensional spaces, and those algorithms that are needed to explore and work in those big problems. And human now I think human models are benefiting a lot from robotics. So yes, I think your question is, can we use the robot to emulate, to do things that can, yes, in addition. But really, I'm just talking about the abstract models that we develop and tools and algorithms. This is fantastic in the areas of human biology.
Okay, thank you very much.